Welcome to the Solar Ute project. This video is an overview of the electronics system of the Solar Ute. As a big believer in open source, all schematics, PCB files, and firmware is available on my GitHub. Check the description below for the GitHub link and my email. At this point, I'd like to talk about the microcontrollers I used during this project. As seen on this overview schematic, the CAN bus is used extensively. So, my favorite family of microcontrollers, the STM32F1 series, dominates as a low-cost, powerful processor, often with built-in CAN bus and sometimes two. In an effort to make the programming more accessible, I used Arduino, specifically STM32Duino. I could just as easily have used the free STmicro provided compiler, STM32. Since I use Arduino, I needed a CAN library. One that could handle multiple CAN ports. There were no available libraries, so I wrote my own. CAN. It's on my GitHub. As a postscript, most of my boards were designed and ordered during 2020 when stock was plentiful and inexpensive. That situation has now sadly changed. If we start at the Nissan Leaf motor and its inverter. The Nissan Leaf inverter is controlled by CAN bus. This is the major deciding factor for choosing the Nissan motor as Solar Ute's motor. So, to get the inverter to spin the motor, we have to send CAN instructions to the inverter. Luckily, thanks to a chap that goes by Celeron55, we have the CAN commands required to control the inverter. A big thank you also goes to Damien Maguire for demonstrating a working model for driving the Leaf motor on the bench. Now, we need some electronics to read the accelerator pedal and send the appropriate CAN messages to the inverter, which in turn spins the motor. This is where the NICE board comes in. Note: while CAN buses are designed for multiple equipment connected, I've opted to only have the NICE board and the Leaf inverter on this CAN bus. Overcautious, but it doesn't cost much for the NICE board to have a second CAN bus. The NICE boards were assembled by JLC-PCB in November 2020. The processor I used is the STM32F107. The STM32F107 is a very capable processor. The feature I was after is that it had two CAN ports. Not to mention loads of memory, I/O, and all the rest. I used 2 amp seal connectors which connects the CAN ports. 12-volt power, throttle inputs. Analog input for brake pressure sensor. Outputs to control pumps. Inputs for key switches, etc. Basically, I wanted to control most everything under the bonnet, or hood, with the NICE board. Okay, further down the schematic we have the CAN I/O board. The board uses the CAN bus to interact with inputs and outputs. Primarily, this is used to drive the car's instrument cluster. As seen in this diagram, the CAN I/O is used to drive the tacho, the temperature gauge, the fuel gauge, and 4 dash lamps, such as oil, alternator, etc. These outputs are all controlled by the CAN bus and can be made to do anything. A good example is that I've repurposed the tacho to not only display RPM but it can also represent kilowatts or amps, etc. using the STM32F103, programmed in Arduino. Look it up on GitHub. Next, we have the contactor. Contactor, CAN, controlled, contactor. As shown in the schematic, this board controls the high-voltage main contactors. It also has the high-voltage pre-charge circuit incorporated. But wait, there's more. It has a pre-charge success detection. So, upon CAN instruction, it will initiate pre-charge, and if it fails to charge the DC link, or power to the inverter, it will send a fail message and shut down the negative contactor. If the pre-charge is successful, the positive contactor is energized. But wait, there's even more. It has a latch function, if invoked, will lock in the contactors. Once latched, only removing 12 volts will shut down the contactors. The contactor makes pre-charging the DC link a simple process and with fault detection. When we started the Solar Ute project, I had no idea where the contactors would be installed. By designing this board, it gave me the freedom to place the contactors wherever I liked. I can even use multiple boards should I desire. Look it up on my GitHub. We now move to CAN BV. The CAN BV board is used to read the main battery voltage and current. Of course, the board has a STM32F103. But to read the 400-volt battery, I've used an opto-isolated and galvanically isolated STM32F1. It has a 12-bit ADC which gives 100 mV resolution. The power to the isolated side of the board is enabled by serial comms initiated from the STM32 controller. The voltage sense circuit is relay isolated and controlled by the STM8 controller. So, when the CAN BV is powered down, the board is isolated from the high-voltage battery. Current sensing is achieved using a HSTS21 split-core Hall sensor. The two measurements are synchronized so it can also provide power and energy readings. These readings are sent to the CAN bus at specific intervals so a Coulomb counter can be achieved. Again, check it out on Github. Moving along, we're now looking at the 12-volt BMS. Just to be different, we ditched the old tech lead-acid battery for a LFP or lithium iron phosphate battery. So this comprises of 4 LFP 50 amp-hour cells. The benefits of using LFP is that they have a long cycle life, better capacity, and can be mounted at any angle. Of course, the downside is we need to be more careful with the charging of the battery. Therefore we need a BMS. We are using the Leaf DC to DC converter that came with the motor. This converter uses the main battery and converts it to an isolated, nominal, 12 volts. Actually its range is 13 volts to 15 volts. So the 12-volt BMS board also controls the DC to DC converter to maintain 13.5 volts. It also ensures that the charge to the battery is capped to say 10 amps. Bypassing the BMS for the moment, we'll focus on the 12-cell BMS monitors. The Solar Ute main battery comprises of 150 lithium titanate cells. A discussion on these cells will be covered in another video. These cells, like other lithium cell chemistries, need monitoring and possible balancing. This board, again, using a STM32F103, monitors the voltage and temperature of 12 cells. 1 mV resolution is achieved reading the cell voltages. As an indulgence, I used capacitive cell balancing. It would have been cheaper to use plain old resistive balancing, but there are some benefits to the capacitive balancing, such as automatic level seeking. A common CAN bus connects all the BMS monitors. Digital isolators are used to isolate the board electronics from the common CAN bus. It's now time to look at the BMS controller, where the NICE board is central to driving the Solar Ute. The BMS controller is central to the car's energy source, the battery. The BMS controller has 3 CAN bus ports. I would have liked to use a STM32F413 microcontroller as it has 3 CAN bus ports. However, due to the great chip shortage, it was easier to use an Arduino Due and a MCP2515 for the third port. The BMS controller scans all the data from the BMS monitors. It controls the main battery charger, will alert the NICE board if cell charge is too low. Wakes up the vehicle's electronics depending on whether it's driving or charging. It will initiate balancing if required.